Hello, welcome to my lab report. I'm Robert Pigue, and I'll be your guide today. In this lab, I had to analyze a video of a mass attached vertically to a spring and tracker and create a model using flow script and fundamental physics principles. The mass oscillates vertically while swinging side to side, and so the motion is in 2 dimensions, so my model needs to reflect that. Along with modeling the motion, I also needed to plot the energy changes. This lab required use of both of our fundamental principles, Newton's second law and the energy principle. Modeling the motion required Newton's second law, and plotting the energy changes required the energy principle. Later, we will go into more detail on the use of these principles. This lab is important for its ability to connect a real-world example, such as the mass on a spring, to the energy principle, helping us relate concrete situations to an abstract principle that dictates how the world works. In my case in particular, modeling the motion accurately was difficult, and while I could get my model accurate in one dimension, I could not get it accurate for both the x and y dimension until I discovered an error in my code. I had miscalculated the relaxed length of the spring. With this problem fixed, I now have much better models. The rest of this lab report is going to go as so. First, I will talk about modeling the motion, along with a question regarding the model. Then I will talk about plotting the energy changes, and the answer to a question about the energy changes. Finally, I will discuss some of my final thoughts and conclusions. To get the motion data from the video, I went frame by frame, selecting the center of mass each time. The motion is perceptibly imperfect, meaning the system is not behaving as an ideal system would. More on this later. By plugging the data into my model, we can compare the motion on a single graph, as well as watch a simulation of the 2 systems going at the same time. The next step in creating the model is to identify the forces at play. In this case, there are 2 forces acting upon the mass, which is the system. First is the force of gravity, which pulls straight down in the y direction with a magnitude of mg, m being the mass, which in the model is depicted as a ball, and g being gravitational acceleration. Then there is the force of the spring, which is equal to negative L hat, which is the direction of the spring, times ks, which is the spring constant, times s, which is the amount the spring has been compressed or stretched. Along with these forces, there are some initial conditions and constants that must be defined, such as the initial position and velocity, the mass, the acceleration of gravity, and the spring constant and relaxed length of the spring. The initial position is found using tracker, and we assume the velocity is 0 because the first point is as the mass is being released. 2 of these constants, however, change depending on how you calculate them. In the formula for k, which reads as k equals 4m pi squared divided by t squared, we know every value except t. To find t, we must take the length of 3 periods from tracker and divide by 3 to get an approximation. However, t changes depending on if you calculate based on the period in the x values or y values, as shown below. Then, because the relaxed length of the spring depends on the k value, the calculation based on the x values and y values will differ there too. Later, we will compare these values with more depth. Armed with our knowledge of the forces, constants, and initial conditions, we can now apply Newton's second law to model the motion by using a loop. The first step is to calculate F net, and then we can use F equals ma, which is Newton's second law, to find the acceleration. With the acceleration, we can use the velocity update formula, and then the position update formula, to find the new position of the ball a short delta t later. Now we must update the values of L, L hat, and S. L is the length of the spring, and as the mass moves, it changes, as does L hat, the direction of the spring, and S, the compression or stretch of the spring. Now that we've updated the position, velocity, and components of the spring force equation, we can begin the loop again, finding these values again, and continuing to model the system. Here are how my model is compared to the system. On the left is the graph found using k and L naught from the x values, and on the right the k and L naught from the y values. The red curve is the motion data from tracker, and the blue curve is what my models predict. These 2 graphs are modeling the motion in the y dimension, and as you can see, using k and L naught from the y values is much more accurate. However, if you shifted the blue curves on both graphs a bit to the left, they would align much more closely. This discrepancy is because the real data and the model start during different parts of the same cycle, stemming from the low frame rate of the camera. Another reason the graphs are inaccurate is due to air resistance, which is present in the video, but not in the models. The spring too is another source of inaccuracy, as springs in real life do not behave as ideal springs do. Here are my models compared to the video in the x dimension. Once again, the L naught and k derived from the x values are on the left, and from the y values are on the right. This time, they both are accurate, but again start at different times in the motion data, causing them to be shifted off slightly to the right. Another reason not mentioned before for why the graphs are inaccurate is the human error present in the tracker when I had to select the center of mass each frame. Here are the periods found from the x and y values, and their corresponding L naught and k values. The y values predict a shorter t than the x, therefore having a bigger k and L naught. The values derived from the y led to more accurate graphs, especially for motion in the y direction, where the model using the k, L naught, and t from the x values was wildly incorrect towards the end. A possible reason for the y values leading to more accurate graphs is that the majority of the force exerted on the mass by the spring is in the y direction, so looking at the y would lead to a more accurate period. The energy principle states that delta E is equal to the energy transfers in and out of the system. To plot the energy changes, I would find the energies after predicting the movement of the ball and compare it to the energies in the prior iteration of the loop. There are 3 energies present: the kinetic energy, the gravitational potential, and the spring potential. The energy principle is satisfied because after setting the model in motion, it does not lose or gain energy, just like how ideal systems described by the energy principle behave, because there is no transfer of energy in or out of the system. The orange line stays at 0 in the graph, reflecting the fact that there is no transfer in or out. We can also see this in the graph by identifying that whenever one of the energies present loses energy, another energy in the system gains energy. And now for some final thoughts and conclusions. I really enjoyed this lab. Seeing the models following the real data is super satisfying. This was also the first lab using the energy principle, and now I have a much better understanding of it after doing a lab. That's all I've got. Thanks for watching.